Hey people, welcome Honors 2 Algebra 1 students. This is your video walkthrough for the performance packet from section 5.7, Systems of Linear Inequalities. All right, the good news, this is the last lesson you are going to learn in the 2019-2020 school year, and that makes us happy. Yay! All right, so and another piece of good news for you, nothing new is being taught here. If you get the last section from 5.6, how to graph a linear inequality, all we're doing in this section is we're graphing two of them at the same time on the same coordinate plane. So procedurally, we're not doing anything different. We're just kind of looking for the solutions to a system of linear inequalities rather than just the solutions to one linear inequality. So remember, a system of equations that we talked about before, system is a fancy word for two of them at the same time. All right, so that's what we're talking about today. We're going to look at two different inequalities. We're going to graph them both, and we're going to find points that are solutions to the system, which means they're solutions to both inequalities. So I thought it'd be a good idea to start with an exploration of kind of like where this is coming from and what we're actually doing, what we're looking for. So let's jump right into it. Exploration 1 says match each linear inequality with its graph and explain your reasoning. So it's always good to start with a little refresher from last section. We have two inequalities here and here, inequality 1 and inequality 2. And we're supposed to match them with our graph. So what's the first thing that we're always going to do if we're talking about graphs of a linear equation or inequality? We got to put it in slope-intercept form. So that's the first thing I'm doing here. Let's just take a look at inequality 1. I did that in red. You can see that, okay, so we got to subtract 2x from both sides, and I always like putting that x term first, so I'm going to slide that negative 2x in front of the positive 4, and we get, and again, we do not have to change the sign because we're not dividing or multiplying anything by a negative number, but that's something you always got to keep in the back of your mind when you're dealing with inequalities. So we have y equals negative 2x plus 4, and that means our y-intercept is positive 4, and our slope is negative 2. So we're looking for a downhill line because our slope is negative, and we're looking for a y-intercept of positive 4. So if we look at this graph, the y-intercept is 0. This is a positive slope. Matter of fact, that's a positive 2 because we rise 2, run 1. This one, a y-intercept of 4, and it's got that negative slope, and it is a negative 2 slope. If we go down 2 and right 1, that's how we get that nice downhill pitch here. All right, so this would be inequality number 1 is A, and of course, by process of elimination, we know that inequality 2 can be matched with graph B, but let's take a look at how we do that. All right, again, both sides, we're subtracting 2x from both sides, all right, and that moves, since we have a 0 as our constant, that's going to be our y-intercept, but we do not need to include it in the inequality right here. I could put plus 0 here, but I really don't need to, all right? So, and then, but remember, this is a negative 1y, so we're not done solving yet. We actually have to get y by itself, so we need to divide both sides by negative 1. And of course, hopefully you're shouting at the video right now, Mr. Schaub, don't forget to flip the sign. Okay, that's what I think my students sound like. Mr. Schaub, oh my goodness. Seriously, that's something that most of us are going to forget because our brains are focused on other things like graphing these inequalities. So don't forget, if you ever have to solve for y and you have to divide both sides by a negative number to do that, you got to flip that inequality sign. It makes a huge difference on where our solutions are in the graph. So anyway, this boundary line here, let me get my lightsaber out again. This boundary line here, it is solid. Notice they're both solid because we're using less than or equal to signs. Now, this one ends up being a greater than or equal to sign, but that line there never changes, it never disappears. So don't drop it. That's another thing I see with students. They go from line to line and they drop that little line underneath. Boy, that makes a difference too, because you're going to end up getting the wrong type of boundary line here. All right, so y is greater than 2x. That means our y-intercept is 0. Our slope is positive 2, so we got that nice steep uphill slope going. And we shade above the line because y has to be greater than 2x, greater than or equal to. So the line is solid, we shade above. Here, y had to be less than or equal to negative 2x plus 4. So the solutions are less than the boundary line, and the boundary line, of course, is included in this one as well. Okay, so in part 2, now we're going to take those two inequalities and we're going to graph them on the same coordinate plane. It says, part A says, use two different colors to graph the inequalities in the same coordinate plane. What is the result? So if we do that, let me remove this big old block here and this, okay? And let's take a look at what happens here. Let's go ahead and delete that too. Why not? Okay, so I've got the blue inequality. Inequality 2 is here. It's drawn in blue and shaded in blue. Inequality 1 is drawn in red and shaded in red. And look what happens here. So since we've got two inequalities on the same coordinate plane, it kind of splits the coordinate plane into 4 regions. Okay, so that's what I said here. All right, it creates 4 regions. The region that is shaded twice, okay, so that would be this area. It means it contains the points that are solutions to both inequalities, okay? It makes perfect sense if you really think about it. The area that's shaded twice, remember, when we shade, that's because we're showing where the solutions to an inequality are. So the area that's shaded twice means these are solutions to both inequalities, and that's what we're looking for when we solve a system. Remember, they got to be numbers that we could put in for x and y that would give us a true statement. So any point in this region that's purple, it should be a solution to both inequalities. Okay, for example, let's use something easy. Let's say I use the point -2, +2. Okay, if I put a -2 in for x and a +2 in for y, both of these inequalities should end up giving me true statements. All right, so -2 times 2 is -4. -4 plus 2 is -2. -2 is less than -4. That's just how you check it. I know I'm going really quick, but hey, it's a video. Go back and watch it again if you had no idea what I just said. But this is basically how it breaks down. Okay, so we've got 4 regions here, and they all mean something different. If there's an area where nothing is shaded, that means these points over here, any ordered pair in this region, and remember, it extends on forever. So it's a never-ending region, but these are solutions to neither inequality. If we take these numbers, we plug them in for x and y, it's going to make both inequalities false, and we don't want those. Okay, so this just red area, that means these are solutions to only inequality 1. If you plug in any of these ordered pairs in for x and y, you'll get a true statement for inequality 1. You'll get a false statement for inequality number 2 because they're not shaded in blue. All right, they're only shaded in red. Same thing for here. This little section of blue up here that's not shaded in red, these are solutions to inequality 2 only. All right, so solutions to just inequality 2, solutions to just inequality 1, solutions to neither inequality, and then this is what we're looking for. This is our golden child right here. The area that's shaded twice, those are solutions to both inequalities. So any point in here will be a solution. All right, so it's as simple as that. If you can graph one linear inequality, then you can graph 2 of them, and you can find the area that's shaded twice. So let's take a look at the rest of the notes, talk about the practice problems and the applications just to get you started, and then that's going to be it. So let's move on to the next page. Okay, so a couple definitions here. I've already got them shown because I don't need to go through these. You hopefully have already looked at my notes. You've taken the notes. You got them written down. You're watching this video just to understand a little bit better. So a system of linear inequalities, like we talked about, it's 2 or more inequalities that use the same variable. So I gave you an example here where we have 2 inequalities that are in slope-intercept form. Okay, that can be a system of inequalities, or they could be in standard form. They really could be in any form. But just remember, if we're graphing them, and the cool thing about systems of linear inequalities, some of you might be worried, like, oh gosh, am I going to have to do substitution or elimination again? Good news, no. You cannot solve inequalities by using substitution or elimination. The only way you can find the solutions to a system of linear inequalities is to graph them both. So we only have one method. You don't have to worry about algebra. Everybody's rejoicing right now. I'll give you a few seconds to just, cheer and jump around, and then come right back and we'll get talking about it. All right. So graphing is the only way we can solve these, because think about it. With a system of equations, we usually just got one answer, like one ordered pair was the solution to both equations. Now, sometimes it was no solution, sometimes it was infinitely many, but those are special cases. We were getting one answer as a solution. With inequalities, we're going to have a whole region full of solutions. So it's not like we can just list those out. There's infinitely many points that would be solutions. So we can only show where the solutions are by visually creating a graph, just like this one down here. You can see we got two linear inequalities. We have the shaded region here. Any point in this region, and remember, yes, it extends in this direction forever. So any points that are down here in the coordinate plane, those also count as solutions. There's, even in this little sliver here, this little pizza slice, there are infinitely many ordered pairs if you count decimals and fractions. So we can't list out all the solutions. We have to show it in a graph. So that's our only method. Okay, so the other two definitions, a solution, we know what a solution is. It makes the inequality true. Remember, we're talking about a solution to a system, so it can't just be a solution to one of the inequalities. It has to be a solution to each inequality in the system. Now, we're typically going to just look at systems that have two inequalities, but you could have 3, 4, 5. There could be a lot of inequalities. You would just graph them all, look for the area that, if you have 3 inequalities, you would look for the area that's shaded 3 times instead of 2 times. It's that simple, okay? And like I said, the graph of the region where all of a system's solutions are located, that is the graph of a system of linear inequality. So this is a good example. It says graph each inequality on the same coordinate plane. That's step 1. There's only 2 steps, so it must be pretty easy, right? And then step 2 is find the intersection of the half planes that are solutions of the inequalities. That, we don't need to use that kind of terminology. So I like writing it in my own words. In other words, find the area that is shaded twice. Okay, if it's shaded twice, that means it's solutions. They are solutions to both inequalities. It's as simple as that. So let's take a look at a couple examples. Okay, I think I got everything I want fit on this window. So example 1 says solve the system of inequalities by graphing. Highlight the solution region. That you don't really need to do. I'm just basically looking, maybe put an arrow pointing to where the solutions are, something like that, to make it super clear. But really what I'm just looking for is the area that's shaded twice. So let's try it out. We got these 2 inequalities here. Y is less than or equal to 3, and y is greater than x plus 2. So I color coordinated these. I decided to use green and orange today. So the first line, this is a special case where we have a slope of 0 and a y-intercept of 3. So this is a horizontal line. All right, so anytime x is not in the inequality, it's going to be horizontal. Anytime y is not there, it's going to be vertical. Remember, we just got to stay on top of that stuff. So let's look at the sign we're using. Less than or equal to means we use a solid boundary line, and we're going to shade below that because it's saying in order to be a solution, the y-coordinate has to be less than or equal to 3. So it could be 3, it could be 2, 1, negative 48, negative a billion, whatever it is. Those are all solutions. So we're going to shade below that boundary line. Okay. The orange equation, y is greater than x plus 2. Well, our slope is 1 because there's no number in front of x, but x is there. And our b value is positive 2. So we are going to use a dotted line because of this sign right here. Where's my, there it is. Greater than means dotted and shade above. Remember, you still have that cheat sheet from the 5-6 notes on which sign means do what to the graph. Boy, I could have worded that better, but hopefully you know what I mean. Let's go ahead and take a look at what the graph should look like. All right, so here we go. We've got our horizontal boundary line here. We use the solid line we shaded below. And then we have our orange inequality right here. This is a slope of positive 1. Starts at the y-intercept of positive 2. And we use a dotted line here because y has to be greater than that boundary line. It cannot be equal to it. All right, so side note, any point that's like this point right here, the point, what is that, 1, 3, okay, is 1, 3 a solution to the system? No. In order to be a solution, both of these lines would have to be solid. If even one of the lines is dotted, then it is not a solution to the system because it would not satisfy the orange equation. This point right here, it would satisfy the green one, but because one of the lines is dotted, that means the line here is not a solution. So any point that's maybe shaded both ways and on a solid line, like on any of these points right here, those are part of the solution, but this point and any point on the orange boundary line do not count toward the solutions. Okay, so The next question is the point -6, -1 a solution to the system? And the answer is yes, it is. Because 6, 1, even though we can't fit it on our coordinate plane, we know it would be, so here's -6 would be about here, -1 would be here. So because it's in that pizza wedge, right? It's in that double shaded area. Remember, this extends forever in this direction and this direction. So all these points out here would also be solutions. So this is in fact a solution, even though we can't fit it on our coordinate plane. We have to understand that all 4 of these regions, the orange region, the white region, the green region, and then this combination, this double shaded region, they extend forever in all directions. So they're all infinitely big. This is the only section we're worried about, though. This is where our solutions are. The rest of them we don't really care about. All right, so why don't you use what I did in example 1, pause the video, take a whack at example 2, and see if you can graph both of those inequalities on the same boundary line and come up with the same graph that I did. And remember, you just want to kind of, if it's not clear which area is shaded twice, then you definitely want to point that out with maybe like an arrow and say, hey, here are my solutions. Okay, so pause the video, try example number 2, and we'll come back in just 1 second. Okay, and I'm back. Hopefully you didn't miss me too much. Let's take a look here and see how you did. All right, so let's take a look here. The green equation, the one I have highlighted in green here, it's already in slope-intercept form, so our slope is -2, our y-intercept is +1, and because the sign is greater than, we're going to use a dotted line, a dotted boundary line, and we're going to shade above that boundary line, okay? Now, the orange equation, that is not in slope-intercept form. So the first thing we're going to do is put it in slope-intercept form. So you can see I got to subtract 2x from both sides, slide that -2x in front of the -2, and that tells us that we have a slope of -2 and a y-intercept of -2. So you may have been sitting at home saying, oh my gosh, Mr. Schaub, we have the same slope on these 2 lines. Something crazy might happen here. You would be exactly right. Let's take a look. Okay, so what happens when we graph them? We get something crazy. Like I said, we don't have 4 regions. We have 2 parallel lines. We're shading above the green boundary line and we're shading below the orange boundary line. So because these 2 lines are parallel, these 2 regions are never going to intersect. There's never going to be an area that is shaded twice. So this is one of the special cases that you got to look out for, and this is really the only special case that can happen. You're either going to have a region of solutions, or if you have parallel lines and you have a situation like this, then you're not going to have a double shaded region. You're just going to have an area. Let me get my pointer out here. You're going to have an area in the middle here where there's no solution. These points are solutions to neither inequality. Over here, these are just solutions to the green inequality. Over here, these are just solutions to the orange inequality. There's no point that is a solution to both. So the answer here is there is no solution. And this can only happen, let me go ahead and erase this, when we have parallel lines. The boundary lines are parallel. Now, remember, if the signs were different, if we shaded above the orange and below the green, then that middle section right through here, this would be double shaded. So just because you have parallel lines, it doesn't mean it's automatically going to be no solution. You just kind of have to graph it correctly, look at the graph and see and ask yourself, is there ever going to be a place in this coordinate plane where the 2 shaded regions come together? Okay, in this case, it's not, so that's why our answer is no solution. Okay, any other lines besides parallel lines, you're always going to have a solution region somewhere. Okay, so that's it, people. I mean, that's it for the notes. Like I said, if you can graph 1 inequality, then you can graph 2, and if you can graph 2, then you can find the solution region. I am going to give you a little help on this video since I literally did not give you any help on my notes packet this week, and that's on purpose because I think I scaled it back a little bit. I took it easy on you guys this week, and you're welcome. You have 6 practice problems, and you have 1 application. So you're welcome. Feel free to send me gifts in the mail, whatever, gift cards, cash, anything like that. Obviously, I'm kidding. Please do not send cash through the mail. In case anybody never taught you that life lesson, I can do that right now. All right, but anyway, let's do number 5 together because these are kind of tricky. You're kind of working backwards to come up with the inequalities that are shown in the graph. So, but basically these are all skills that we already have. We're going to take a look at that line. First, we're going to figure out what the boundary line is, and then we're going to figure out what sign we should replace the equal sign with to make sure that, you know, if it's shaded above and a solid line, we've got to use the right sign. Okay, so I'm going to use blue for, you can see what line I'm referring to here. I'm going to use blue to represent the information for that solid inequality graph there. All right, so with that line, our slope, let's see, if we start, well, first of all, let's start with the y-intercept. The b value is +1, and the slope, let's see, let's get my laser pointer out here. We start at +1, and we rise 1, run 1. So that would be +1 over +1, or just 1, okay? With the red line, or the other inequality, the dotted line inequality, I'm going to do it in red. We are going to find our b value first, which is also a +1. So that's okay. If the y-intercepts are the same, that doesn't really mean anything about the graphs. It just means that they both meet, the boundary lines meet at that point. Our slope on this one, you can see here, it's a negative slope because it goes downhill. So we go down 1, right 1. So that would be let's see, in fraction form, it would be -1 over +1. So basically, this slope is a -1. All right, so let's go ahead and write our two inequalities. I'm going to write them as equations first, just to show you. This is probably the best way to do it. The first one would be y equals 1x. So I'm just going to put x, right? We're using a +1, so we don't need to put that in there. You certainly can if you want to. +1, because the b value is 1. All right, and then the red inequality, that's going to be y equals, and remember, it's not going to end up as an equal or as an equation. I'm just putting those in as placeholders because this is what the boundary lines are. So it's going to be -1x plus 1, okay? And now I'm going to erase those signs because now we got to figure out what inequality sign to put in here. So the blue equation is a solid boundary line, so we know it's going to be either less than or equal to or greater than or equal to, and then we shade above, so it's got to be greater than or equal to. So I'm going to put in greater than or equal to for that one. And now let's look at the other inequality. It's a dotted line, so it's either going to be less than or greater than. It's not going to have the little line underneath it like this one does. And we're shading below that line, so below means less than. Let's go to the pen. We're going to put a less than, and it's not going to be less than or equal to because of the boundary line is dotted. So there we go. We got our answer. I'll circle it in green. All right. This is the system represented by that graph in number 5. So we're just kind of working backwards, finding that information about the lines and using that to create the boundary line. And then just kind of looking at the shading and the dotted or solid to figure out which inequality sign we use there. All right, so that's number 5. Hopefully you can use that to do number 6. Okay, and like I said before, let's move on to the application. You got one application to fill out. Before I get started with this, yes, you do need to do the extra part, okay? Answer that question. It won't be that difficult. I think you can figure it out. And if not, come to my Zoom session or watch the Zoom session video because I surely will be talking about how to do the rest of this problem in that session, all right? But as always, try it on your own first. Get help if you need it, all right? You can teach yourself this. You can do it. You can apply these skills on your own, all right? I got faith in you. All right, so I'm going to help you in this video by helping you set up what the system of linear inequalities is, linear inequalities, and then you can hopefully take it from there. So I color-coded this information that they gave us, okay? So let's read first, and then we'll break it down. What's Up Toys is a small toy company that specializes in toy cars and toy trucks. The people at What's Up Toys are confident that they can sell all the toy cars and trucks they make. But there are 2 constraints that limit their production today. All right, so each day, this is kind of what they are dealing with here. I'm going to zoom in a little bit, all right, so I can write. But there's 2 situations, 2 constraints that they need to meet. They only have 360 wheels in stock, and they only have 100 seats in stock. So if that's all they have, then they got it. Basically, constraints mean their limits on what can be produced every day. All right, so let's start with the wheels information. Each car needs 4 wheels and each truck needs 6 wheels, and they have 360 wheels in stock. Now, down at the bottom down here, you can see X represents the number of cars and Y represents the number of trucks. Now, as you know, when you start an application, the first thing we do is define the variables. They did that for us. That's very nice of them. We're going to thank them, and we're going to take that and run with it. So if X is the number of cars, and each car needs 4 wheels, then we could say the number of wheels needed to produce cars would be 4 times X, okay? 4 wheels times the number of cars that need those wheels. Similarly, for the number of trucks, each truck needs 6 wheels, so it's going to be plus 6y. Okay, so basically 4x plus 6y, that is the total number of wheels needed to produce cars and trucks. And remember, that cannot go over 360. It can be equal to 360 or it can be less than 360, but it cannot go over. So the sign we need to use is less than or equal to. All right, so, and then that's going to be where you always put the total on the back end of the inequality. All right, so basically we're saying 4 wheels per car plus 6 wheels per truck has to be less than or equal to 360 because that's all they got. So they cannot produce cars and trucks that require more than 360 wheels. Okay, so let's do the seats inequality the same way. All right, each car needs 2 seats, so 2 seats times the number of cars, plus each truck needs 1 seat, so plus 1 times y, and that has to be less than or equal to 100. Okay, so you can see that right here. All right, 2x plus y is less than or equal to 100 because they only have 100 seats. Each car needs 2 seats, each truck needs 1 seat. So there we go. That is your system of linear inequalities. You are responsible for graphing both of those inequalities. So what are you going to have to do? You're going to have to put these in slope-intercept form. All right, so make sure you do that first. You know, show all your work on this. Obviously, I always want you to do that. And then once you have them in slope-intercept form, you should be able to graph them both on this coordinate plane and then use that information to maximize their efficiency, maximize their profits. Isn't that what every company always wants to do, is make as much money as possible? Exactly. So you can see the type of applications that these have. Businesses deal with constraints and limitations on production every single day that they're in existence. So this is a perfect application that's going to demonstrate the usefulness of systems of linear inequalities like this. Is it simplified? Sure, but hopefully you get the process and you get the picture of how these can be used. So that's it for the video. Like I said, come to the Zoom session if you're still having trouble with this application. But it should be short and sweet this week, people. I'm telling you. So have a little confidence going into it. Get it done early. Ask questions. You know how to get a hold of me. Good luck. Have an awesome week. I'm out. Later.